Okay, here we're going to move on to the idea of probability. In many sample spaces, all the outcomes or simple events are equally likely. These are the simplest sort of sample spaces, and often we will choose an equally likely sample space over some other sample space if we have that option. Okay, in this case we can use something called the equally likely assumption. If all events in a sample space are equally likely to occur, the probability of each is 1 over n, where n is the number of simple events in the sample space. Okay, from the equally likely assumption, we get a basic principle of probability. If we have several simple events in our event, our compound event, what we can do is count them and take that number, divide by the number of items in the sample space. Just a little note on notation. I think we've mentioned this before, but just in case we haven't. N of e, this is a function. Recognize your function notation from algebra. Instead of f of x, we have n of e. What this means is the number of elements in the set E. So we take the number of elements in the set E and divide by the number of elements in the sample space in order to get the probability of event E. Let's do some examples. Let's suppose that we flip 2 fair coins. What's the probability of getting? Okay, we have several events here that are possible. Okay, before we can calculate any probabilities, we need to set up our sample space. I will call the sample space S, capital S. Okay, and we want to have a little bit of an order here. If we think of these as being ordered pairs in some sense, like for example, you might have a dime and then a quarter. Okay, I know it doesn't say the 2 coins are different, but this will help us to think of the possibilities of if we throw them down or flip them, what are the possibilities for the dime? We could get heads or we could get tails. What are the possibilities for the quarter? We could get heads or we could get tails. So we could get heads on the dime, tails on the quarter, or we could switch them and get tails on the first one, heads on the second. Okay, and of course, whether it's a dime or quarter, one of each, or 2 dimes or 2 pennies, actually is not relevant to our problem, but it helps us to think about it so that we can write down the sample space. So we could have HT and TH, and these are not the same. In other words, if we had 2 different coins, we would notice, okay, head on the dime, tail on the quarter, tail on the dime, head on the corner. These are not the same possibility. So both of these need to be listed in our sample space. What else could happen? We could get heads on both coins, or we could get tails on both coins. Are there any other possibilities? That's pretty much it, right? That's our sample space. So we want to write down probabilities for each of these. Okay, so if we look at A, let's first write down our event. Okay, 2 tails. So there's only 1 item in it. So what is the probability of A? Well, it's going to be the number of elements in A divided by the number in the sample space. So how many are in A? 1. How many are in the sample space? 4. So our probability is 1/4. Okay, let's suppose we have at least 1 head. Okay, so here, what is going to be in our set? Well, it could be HT, it could be TH, or it could be HH. All of these have at least 1 head. TT has 2 tails, so it would not qualify. So what is the probability of B then? Well, we're going to take the number of elements in B the number of elements in the sample space and divide. The reason we can do this is because each of these is equally likely. Fair coins means heads, tails, equally likely. Okay. So here we have 3 in our set, and we have 4 altogether, so 3/4 would be the probability that we're looking for. Okay. Exactly 1 head. Okay, so what sets have exactly 1 head? I would say HT has exactly 1 head, TH has exactly 1 head, HH has 2 heads, so it doesn't qualify. So the probability of C then would be, we take the number of elements in C, divide by the number in the sample space. There's 2 here. There's 4 in the sample space. 1, 2, 3, 4. So our probability is 1/2. If you did this a whole bunch of times, flipping 2 coins, you would expect that approximately half the time you would get exactly 1 head. Okay, so 2 heads or 2 tails. So this event we would do HH or TT. And so what would my probability be? Okay, once again we take the number in our event divided by the number in the sample space. So this gives me 2/4 or 1/2. 3 tails. So every event that we write has to be a subset of our sample space. So which of these have 3 tails in them? Do any of them? No, none of those have 3 tails, because I can't get 3 tails if I only flip 3 coins. So what would I write down for my event? Empty set. Remember, that's the set with nothing in it. It's got to be a subset of our sample space. If we're going to write down the event, we have to write down empty set. So then, what's the probability of this happening? It's going to be the number of elements in my set divided by the number in the sample space. Well, how many are in my set? Well, it's empty. There's nothing in it. So there's 0 elements in there. 0 divided by 4 is 0. We call this, there's a term for it that we've covered before in an earlier section. We call this an impossible event. Make sure you remember that term. An impossible event if your subset is the empty set. If your event encompasses the entire sample space, everything without omitting any of them, then we call that a certain event. Okay, something we should notice is that all our probabilities are going to be between 0 and 1 inclusive, meaning we allow for the possibility of it being 0. We allow for the possibility of the probability of 1. Okay? If our probability is 0, then it's an impossible event. If our probability is equal, this should be an equal sign. If our probability is equal to 1, then we have a certain event. Let's move on. Okay, let's suppose that we draw a single card from a standard card deck, and then we want to figure out the probabilities of these various events. Okay, first of all what is our sample space going to be? Well, what are the possible outcomes if we draw a single card? Well, all the possible normal cards. What do I mean by normal cards? I just mean we're talking about a standard card deck instead of some specialty deck. So we might have the ace of diamonds, 2 of diamonds, 3 of diamonds, and so on. I'm just going to describe them here in words, the set of 52 cards. Okay, and so how many elements are in our sample space? 52, right? Okay. So let's let event A be the card is a spade. Okay, and so what is in my set? Okay, so we would have the ace, 2, 3, 4, up to 10, jack, queen, king, all of spades. Okay, let's figure out the probability that this occurs. Okay, so we want to get the number in A divided by the number in the sample space. The number in the sample space is certainly 52. How many are in A? Well, how many are going to be in each suit? Well, ace through 10 gives us 10. Jack, queen, king is 3 more. So 13 over 52, which reduces to 1/4. If you think about it, 1/4 of the card deck is spades. So that answer certainly seems reasonable. Okay. Let's let Q be the set of queens. So we're going to have the set of queens in each suit. Okay, so that means we're going to have the queen of diamonds, right? The queen of hearts, the queen of clubs, and the queen of spades. Okay, so the probability of getting a queen will be the number of queens divided by the total number of cards that are in our sample space. So that gives me 4 out of 52. Reduce this 1/13. So since each suit has 13 cards, 1 out of every 13 is a queen. Again, that answer seems reasonable to me. Okay, let's let B be the set of black cards. Okay, the probability of B then will be the number of black cards divided by the total number of cards. How many black cards are there? Well, there are 13 clubs and there are 13 spades. So 13 plus 13 is 26, right? Out of 52, or 1/2. Does that answer seem reasonable? Half the cards are black, half the cards are red. If you hear my dog barking in the background, I apologize. Okay, let's look at the probability that we get something that's higher than a 7. And we're going to assume that aces are high. We're just going to call this set D. So this is going to be the set of higher than a 7. So 8, 9, 10, jack, queen, king. Aces are high, so we've got to put those in too of each suit, right? Okay, so the probability of this. Okay, so we want to figure out the number of cards in D, and we're going to divide by 52. Okay, let's see, how many do we have? 1, 2, 3, 4, 5, 6, 7 in each suit, so 28 over 52, which will be, divide them both by 4, so that'll be 7 out of 13. Again, notice the way that I came up with the 7. I counted these. There's 7 in each suit. Each suit has 13, so it makes sense that our answer would reduce to 7 over 13. Okay, let's roll a single die and let's figure out some probabilities here. Okay, let's look at our sample space first. What's our sample space? It's going to be the set 1, 2, 3, 4, 5, 6. We've encountered this before. What's the probability that we get a 5? Okay, well, what's our event? Just the number 5. Okay, so take the number in your sample space, divide by, take the number in your event, divide by the number in the sample space, and we should note and check. We can only do this if everything is equally likely. Are all these 6 events equally likely? Yes, as long as we have a fair die, which it seems reasonable to assume. In the absence of any other information, we can assume that these are all equally likely and that we have a fair die. We only have 1 in our event. Divide by the number in the sample space, so we get 1/6. Okay, let's look at the prime numbers. What prime numbers are there? 2, 3, 5. Remember, 1 is in a category of its own. It's considered neither a prime number nor a composite number. And so here, the probability of B will be 3/6, or 1/2. Multiple of 3. What numbers here are multiples of 3? 3 and 6. We have 2 of these, so the probability that this occurs will be 2/6, because there's 2 of these, or 1/3. Does that make sense? I hope this is helping. Okay. A number larger than 10. Okay, so what numbers in our sample space? Our event has to be a subset of the sample space. Remember, what numbers of these are larger than 10? Any of them? No, none of them. So what do we put? Empty set. So what is the probability of D then? The number of elements in D divided by the number in the sample space, so this will be 0/6, or just 0. Okay, you don't really have to do any calculations to come up with that. We already know that it is an impossible event to get a number larger than 10 when we roll a single standard die. Okay, let's look at the next one. A number smaller than 10. So what numbers in our sample space qualify as being smaller than 10? Well, all of them are smaller than 10, right? So what is our probability? Well, we take the number in our event divided by the number in the sample space. 6 in our event divided by 6 in the sample space, which gives us a probability of 1. This is what we call a certain event. Without a doubt, when we roll that single standard die, we are going to get a number that is smaller than 10. Okay, I hope this helps you get started with probability. We'll see you next time.